Welcome to The Explainer. Today, we're diving straight into a material that sounds like pure science fiction, but is actively reshaping our world right now: aerogels. If you're interested in the future of sustainable engineering, advanced space exploration, or just how we can radically optimize energy efficiency, you are in the exact right place. We're going to look closely at how this incredibly unique material fundamentally prevents thermal loss, working our way from its microscopic molecular structure all the way up to massive real-world applications.
To kick things off, let's think about a central paradox that we're going to unravel today. How do you stop heat from escaping when your insulation is quite literally up to 99.98% air? It sounds completely counterintuitive, right? Normally, we think of thick, heavy, dense materials as the best barriers. But today, we're going to explore the molecular magic of aerogels and discover exactly why a material composed almost entirely of empty space is actually the greatest thermal insulator humanity has ever engineered.
Part 1. The ultimate thermal insulator. To truly understand the physical properties of this synthetic ultralight solid, we have to look at its makeup. An aerogel starts out as a gel, but the liquid component of that gel is entirely replaced by a gas. What you're left with is a highly porous structure that can be anywhere from 90 to 99.8% air by volume. If you were to hold a piece of standard silica aerogel in your hand, it would feel a bit like fragile, rigid styrofoam. But despite its incredibly low density, it boasts a thermal conductivity as low as 10 to 20 milliwatts per meter Kelvin. To put that into perspective, this dramatically outperforms traditional insulation materials like mineral wool or polyurethane foam. It's an absolute structural marvel.
Part 2. The science of trapping.
So how is this magic material made? It's done through something called the sol-gel process. Step 1 is gelation. This is where solid nanoparticles dispersed in a liquid agglomerate together to form a continuous three-dimensional network. Step 2 is network perfection, where curing and aging strengthen this cross-linked macromolecule frame. But step 3 is where the real engineering trick happens: supercritical drawing. If you just let the liquid evaporate normally, capillary action and surface tension would completely crush that fragile gel network. Instead, scientists use extreme heat and pressure to push the liquid into a supercritical state. This exchanges the liquid for a gas without ever crossing the liquid-gas phase boundary, brilliantly preserving the delicate nanoporous dendritic microstructure.
That perfectly preserved nanoporous structure is entirely responsible for something called the Knudsen effect. This is a reduction in thermal conductivity in gases when the size of the cavity containing the gas becomes comparable to the gas particle's mean free path. Because the pores inside an aerogel are extremely tiny, we're talking usually under 100 nanometers, they literally restrict the movement of the gas particles trapped inside them. By preventing these gas molecules from moving around freely, you completely eliminate convection as a method of heat transfer.
To see this physics in action, imagine putting a highly energetic bouncy ball into a tiny, tightly constrained box where it just doesn't have the physical space to build up any momentum. That's what's happening here. Because of the Knudsen effect in a 30-nanometer aerogel pore, the thermal conductivity of the trapped air drops from a standard 25 down to just 5 milliwatts per meter Kelvin. The microscopic pores are so incredibly small that the air itself becomes a drastically better insulator than it is in an open room. The aerogel is essentially trapping heat by trapping the very molecules that would normally transfer it.
Part 3. Stopping residential heat loss. Now, why does all this nanoscale physics matter to us on a practical level? Well, it's encapsulated in this single staggering number: 40%. The global building sector is currently responsible for roughly 40% of our total global energy use and a full third of energy-related CO2 emissions. We are losing a massive amount of energy just trying to keep our buildings warm in the winter and cool in the summer. Improving thermal performance isn't just a fun science experiment, it is an absolutely critical, immediate priority for sustainable global development. When you run dynamic simulation data comparing the annual heat loss of standard baseline insulation against aerogel-enhanced envelopes, the difference is night and day across various climates. Take a cold climate like Oslo, for example. Both walls and windows are massive sources of heat loss in the winter, but aerogel insulation cuts that wall-related loss nearly in half. Conversely, look at a hot, arid climate like Tashkent. There, the cooling demand completely dominates, and the biggest problem is solar heat gain through the windows. Upgrading to aerogel glazed windows drastically reduces that window heat load.
By strategically applying aerogels based on the specific climate, the real-world results are just massive. We see a 41% reduction in total HVAC energy demand in cold climates like Oslo, a 31% reduction in temperate climates like Madrid, and an 18% reduction in hot, arid climates like Tashkent. Aerogels are highly adaptable. Whether you pack them into structural wall blankets to stop winter heat from escaping, or embed them into transparent window glazing to stop summer heat from entering, they provide an incredibly high-performance solution that slashes CO2 emissions.
Part 4. Extreme cryogenic applications.
Designing insulation for liquid oxygen at 90 Kelvin or liquid hydrogen at 20 Kelvin requires intense, demanding levels of performance. NASA utilizes several aerogel systems for this exact reason, from bulk fill beads to reinforced composite blankets. What you should really take away from this is how tailorable aerogels are. Compared to conventional polymeric foams or cellular glass, aerogels offer unique advantages for cryogenics because they avoid major problems with weathering, mechanical damage, and moisture. They are naturally hydrophobic. That means they don't cryopump or accumulate crippling moisture the way standard foams do when exposed to extreme cold.
When engineers are designing cryogenic systems, they often rely on vacuum jackets. Under a perfect high vacuum state, traditional multi-layer insulation, or MLI, sets the baseline for performance. The problem is vacuums degrade over time, and they are incredibly expensive to maintain on massive storage tanks. That's exactly where aerogel shines. In soft vacuum or completely ambient pressure environments, aerogels drastically outperform all other competitors. Because of that Knudsen effect we discussed earlier, they minimize gas conduction so effectively that they provide unmatched thermal shielding for things like liquefied natural gas storage and liquid hydrogen launch vehicle tanks, even without a perfect vacuum.
When mapping out effective thermal conductivity against cold vacuum pressure, the ultra-low density, or ULD, aerogel blanket really stands out. Across the high to moderate vacuum ranges, it achieves the lowest thermal conductivity of the aerogels tested. It beautifully maintains its structural integrity and limits thermal transfer, proving exactly why layered composites of aerogels are becoming the gold standard for complex, multifunctional cryogenic systems.
Part 5. The future of aerogels. The future applications here are truly staggering. NASA has already used aerogel to physically capture hypervelocity cosmic dust on the Stardust spacecraft without vaporizing the particles, and they use it to insulate the Mars rovers from the freezing Martian nights. Back on Earth, material innovations are actively solving aerogel's traditional brittleness. We are now seeing flexible polyimide aerogel films and composite aerogels integrated with cellulose nanofibers to greatly improve mechanical durability. We are even seeing transparent aerogels inside smart windows that maintain 85% visible light transmission while entirely blocking thermal gain. This is quite literally paving the way for true net-zero energy buildings.
Which leaves us with this final, pretty provocative thought. If a material that is mostly empty space can virtually eliminate thermal loss, from residential homes in Oslo all the way to liquid hydrogen tanks at NASA, what industry is it going to revolutionize next? The processing techniques are becoming more scalable, the costs are dropping, and the potential is definitely boundless. Thank you so much for exploring the science of aerogels with me today. Keep asking questions, keep looking at the data, and we will see you in the next experiment.